Okay, so let's just prove this lemma. Then we want to talk about next step up after finite sets. So we have to make sense of what that means and all that. We'll see. So let's prove this lemma. And we're going to do it by induction. Okay. So let P of n be the statement. If x is contained but not equal to n, and there's no one-to-one f from n to x. Okay, so first of all, we do the base case. P of 0 is vacuously true. Maybe we should investigate to make sure. What does it mean, but not equal to the empty set? Then here is x. Okay, and we need to show that this is true, and it is and implies. And notice this part of the implies is always false. Okay, there's no proper subset of the empty set. So whatever I write here doesn't matter. This is never true. Okay, so this is vacuously true. So that's P of 0 is fine. Now let's assume P of n for some n. Okay, and now let x be a proper subset of n plus 1. Definition of n plus 1 is just n union singleton of n. Okay, and we have to show that there's no one-to-one function from n plus 1 to x.
Sorry, sir, we're not seeing the parts on the far right.
The top sheet, yeah. Sorry about that. Okay, yes, I now see it in the chat too. Okay. All right, so now we have to do our induction step. We have to show that there's no f from n plus 1 to x. So as usual with things involving like n plus 1, there's like two cases. Well, to the case where x is a proper subset of n. Okay, so there's kind of like two possibilities. Either n is in x, or n is not in x, in which case x is a subset of n. Okay. So actually this turns out to be the easier thing. So if n is an element of x, let x prime just be like take all the elements of x except for n. Okay. Okay, the other case, actually, you know, I'm splitting up into cases too soon. So let me go back. I think it is something, but I should have said we should have been going for a contradiction. Okay, so let's go for a contradiction. suppose f from n plus 1 to x is 1 to 1, and we're going for a contradiction. Okay. And again, x is a proper subset of n plus 1. Okay, so what we really should do is we should look at, so just as an aside, n plus 1 is n union n. So we should like, it's kind of like, what we want to do is find a, so yeah, this is what we do. We want to find a proper subset x prime of n and a function g from n to x prime. So what we should do is not break into cases, but we should let x prime just be x and take away f of n. Okay. And the only problem is that it might be that oh yeah, we shouldn't do this. We should do something else. Yeah, we want to find a proper subset of n. So we should see if f of x equals n for some x in n plus 1. Yeah, that's what we should do. Okay. Oh, sorry. I think I'm confusing things a little bit here. But let's just see how it works out. Okay, so if f of x equals n for some x in n plus 1, then what should we do? We should try and like fix things so we get a map from n to x. Okay, so we should define g from n to something by well, we should say like g of y equals f of y if y is not equal to x. No, I'm not quite getting it to work out correctly. Unfortunately. Let's see. So probably what I should do is come back to this lemma in like some quick 5-minute video. I'm just like not getting it right. Okay, so let me just tell you. To be continued in a separate video. Okay. So let me just continue by assuming the lemma and see what the kind of things that we get from it. Okay. Basically, from this lemma, we get all the things about, we just make sure that all the things about cardinality kind of are making sense. Like we have this proposition. Okay, oh, sorry, I missed something in the chat. Let me just see. Oh, let's see. So just to responding to this question in the chat, let me try and write the question in the chat. If X is a subset of n plus 1, oh, then is X an element of n? Oh, so then is it true that X is an element of n or X equals n? That's almost true. What the normal thing is we say like X is an element of n plus 1, then X is an element of n or X equals n, not subsets. Just to see the difference, look at n equals 4. This is 1, 2, 3. Okay, now 4 plus 1, that's defined to be 4, union the singleton 3, 4. In other words, 4 plus 1 is just 5. Okay. And now you see like the elements of 4 plus 1 are 0, 1, 2, 3. These are all the elements of an element of 4 plus 1 is either equal to 4 or an element of 4. On the other hand, you can have a subset, like there's lots and lots of subsets of 4 plus 1, 2, 3, 4. This is a subset of 4 plus 1. Okay. This is not like a natural number, but the lemma tells us that the cardinality of this set has to be less than 5. Okay. Yes. Okay. So just to make sure, yeah. But I think it's good you asked that question. It makes me think that you are studying, because that will definitely something to know. That is the definition of, well, like that comes from the definition of old, not this symbol. Okay. Right. Okay, so I hope that I'm able to fix the proof of that lemma just in a different video. So as an application of the lemma, we have this proposition. Suppose you have natural numbers n and m, and suppose n is not equal to m, then there's no one-to-one and onto f from n to m. Okay, that's the first part. 2, if the cardinality of S equals m, and also the cardinality of S equals n, then actually n equals m. Okay. And 3, the natural numbers is an infinite set. Okay. So this is kind of reassuring us that cardinality and natural numbers are kind of matching up. Okay, so proof. Okay, so we know that any two natural numbers are comparable. So we know either n is less than m or m is less than n. The other possibility is that n equals m, but we're supposing that's not true. Okay. Okay. So if n is less than m, there is no one-to-one f from m to n by the lemma. That's what the lemma says. And that's because since n is a subset of m, or a proper subset of m. And if m is less than n, there's also no one-to-one function from n to m. Okay, this requires us to know we need the fact that if n is an element of m, then n is a proper subset of m. Okay, you can prove this. This uses the fact which comes from the fact that a natural number is a set of all natural numbers okay. It comes from the fact that a natural number consists exactly of the natural numbers that are less than it. Okay. Okay. And so now, since if n is less than m, it's a proper subset of m. So there's no one-to-one function from m to n to n. Okay. Okay, and if m is less than n, it's the same proof of, with m and n switched. Okay. Now for the second part, if the cardinality of S is both m and n, it means we have a one-to-one and onto function from m to s, and one-to-one and onto function from n to s, and then you can join those up to get a one-to-one and onto function from n to m. Okay, so for part 2, take f from m to s, g from n to s, and look at what, like g inverse of f, and that goes from m to n, is one-to-one and onto. For example, okay, so proving that there's a one-to-one and onto function from m to n, which is impossible unless n equals m. Okay, and then for the third part, we need to show that n is an infinite set. Okay, so for part 3, suppose f from n to the natural numbers is 1 to 1 and on to oh, I guess I should switch these around. So let's switch them around. So I have 1 to 1 function, 1 to 1 and onto function. Okay. Now look at the function from let's call it g from n plus 1 to n, defined by g of m equals f of m for all m in n plus 1. In other words, g is just the restriction of f to this n plus 1. Okay, since g is the restriction of a function, it's also 1 to 1. And but n is a proper subset of n plus 1, so this is impossible by the lemma. So this shows that n is infinite. Okay, that's the end of that proposition. Okay, and I guess there's a good place to stop. So I guess now is just to remind you about the exam tomorrow. I know you've said that you can't possibly forget, but maybe there's someone who didn't remember. Anyways, okay, so oh yeah, just to tell you, any questions about the exam you have, I'm happy to answer them the best that I can. Okay, so when you're working on the exam, please feel free to email me. Yes. Okay, so that is it. Yeah, just everyone, just, try to get some rest, I guess. And I won't really see you tomorrow, but if it were a real exam, I would see you tomorrow. So, okay, anyways, yep, that's it. So good luck, everyone. I'll next see you on Wednesday. Okay, so bye. Okay.